think I have the window open that I want to tell them. Well, let me review this just because we do have new students. One new in the day, and we've had others join us. So pulling up, just going to show this real quickly, just for the benefit of folks new to the class. Our Google Classroom, of course, you know where our Meet link is that we join. Our curriculum is found at this link right above it, Quick Links Buzz. That's where we find our algebra. That's where we find our class. And that's what we'll be looking at today. So if you're new to the class or anyone still getting familiar with it, just showing you how to get to Buzz quickly. That's the easiest way to get there. So we'll be looking at that in just a minute after we get everybody in here. All right, we've got a lot of folks in here, still missing quite a few, so I'll give it another minute or two. We got a lot to cover today. Seems like I say that every class, but I don't know. We just always have a lot to cover. It's Algebra II. There's just a lot of stuff that's in this course that we got to get through in a school year. But hope you had a great Halloween. Hope you have lots of treats left over laying around the house to help fatten yourself up and get ready for Thanksgiving. Right, that's what Halloween is. It's just getting used to eating more. Right, put a lot of candy in there to expand the belly a little bit. Get ready for some big feasting on Thanksgiving week when we have lots of like pies and cakes and desserts and sorts. You know, oh, and some like turkey and mashed potato stuff too. Stuffing and gravy. That's what I look for at my place. But I'm happy to be back. I was out Friday. You may have seen the message in Google Classroom or got the email that I was ill. I thought I had the flu. I felt like I had the flu, had all the symptoms of the flu, but it turns out it was a strep infection. I had strep, so I had to go to the doctor and get some antibiotics, which I've been on. This is my third day, I guess, of antibiotics, and I feel 75, 80%. I'm going down here a little bit as the day goes along, but I'm doing a little better. A couple hours ago, 3 hours ago, I was pretty dizzy. I had to lay on my couch here in my office for a little bit, just to kind of give myself a break. But this is my last class of the day. So after this, I can go home and lay down and take one more antibiotics tonight. I think another day or two, I'll be feeling great. So this is a B day week. So on Friday is B day. So we only have Wednesday. Keith's experiencing an earthquake, but the rest of us are doing well this November. It's November already, which means it's not long until the end of the semester. Because, wow, we're getting there. But most people in here are staying caught up pretty well. I think we just have a student or two that is behind some assignments, but I got to say most of this class, and I'm just based on history. Algebra 2 is a class that struggles. Usually in Algebra 2, I'll have 6 or 8 students that are just fighting to keep up, and their grades are in the garbage dump right now, and they're hoping to pass the class. I do not have 6 or 8 students in that situation, and I'm usually talking about each of my Algebra 2 classes. I have more than one Algebra 2 class, and usually each class I've got about 6 kids at least that are struggling. You guys are doing great. I got to say, we've got a student or two. And let's see, looking at both my Algebra 2 classes, I have just a couple of students that I'm worried about will not pass this semester. Usually I've got like 10, and I'm like, oh my gosh, how are these guys ever going to get caught up? Thanksgiving break usually helps because you've got a week of no classes. And if you dedicate it and sit down and say, okay, I'm going to need to use Monday. Monday's a throwout day, right? We don't do anything on Monday on Thanksgiving week. If you go travel, see family, that's usually later in the week. Sit down and get a bunch of stuff turned in, like on that Monday. But hopefully you can get a bunch of stuff turned in between now and Monday if you're behind, and just enjoy a full 9 solid days of nothing, because, that's what it should be. Just a time to relax, see some family, give some friends, play some games, eat some food, watch some movies, get ready, get your Christmas tree put up. So my daughter already has the Christmas tree put up. They put it up yesterday, and they said they were a day late because I guess traditionally his family always put it up on the 1st. But I guess my daughter made him wait a day because we don't put it up on the 1st of November. We got a few folks who need their cameras on. Camden, you're struggling with Wi-Fi. Leave your camera off because I think I'd lose you altogether. Uh, great, great, great. You will want to take some notes, guys. We are working with quadratics, but we're getting in some areas of quadratics you're not really familiar with. We're used to just basic quadratic stuff. We're gonna look at a lot of different stuff with quadratics today, and you want to have some notes on this because we're gonna have a test on it here in a few weeks. Let's see what our buzz shows us today. All right, here we go. Let's go to the grade screen as usual. I'll just click on the icon up here. This week, we are down to lessons 4 and 5, graphing quadratics and completing the square. This is where you're really going to want some notes. Completing the square is not hard unless you don't have any notes and have no idea what you're doing. As long as you know how the process works, it's not that hard. You just have to understand how the process works. But you should have everything done through 3.03. That's what we did last week, 3.03, 3.02. We've got solving quadratic equations and quadratic equations with complex solutions, which means imaginary solutions. And then we'll test right before we take Thanksgiving break, because I don't want you to learn all this good stuff and then take a week off before you test. So next week we'll finish up our lessons on quadratics and we'll have a test right as we go into Thanksgiving break. So we're to look at 3.04 and 3.05 today. So let's go back to the activity screen where we started and look at the lesson for graphing quadratics. I do have Desmos open here. We're ready to do some graphing. Some of this talks about graphing it on paper. We're not going to pay a whole lot of attention to that since this is a virtual class and we do have access to desmos.com for all of our graphing needs. But let's look a bit. Parabolas in your life. And there are lots of parabolas around us in everyday life. What do these 5 images have in common? We got this bridge and this satellite dish, and we have the Eiffel Tower. You have this kid drinking out of this lawn sprinkler, and someone kicking a soccer ball. Hemisphere. Oh, let's see. Well, look, the little red kind of highlights. They all have a parabola shape involved with them. That's the bottom of the Eiffel Tower support. A ball makes a parabola arch as it's kicked. You know, there are parabolas around us all the time, whether we notice them or not. So here's what we're going to learn. In what ways does adding a constant or a coefficient to a quadratic equation affect the graph? How are the axis of symmetry and vertex related? And what key features of a quadratic graph can be identified? And there's several key features we're going to look at. That's where you're going to make some notes. So up until this point, the majority of graphs have been focusing on lines. You know, and when we get first into algebra, and we spend a lot of time just looking at lines derived from linear equations. You know, y equals mx plus b is our most common equation we use that we can graph. But when we get to quadratic equations, the simplest quadratic equation is just f of x equals x squared. X squared is the simplest. There's a graph of it, x squared. You can graph it by substituting values in for x and finding what the y is. Put -2 in. When you square -2, you get 4. So that means the point -2, 4 is on your graph. So they put that in there. So this is showing how you would graph this parabola by hand, just by making a table, substituting in -2, -1, 0, 1, 2, and being able to make a parabola on the graph. So that illustrates a quadratic equation in standard position. That means with no translations. That's just the most simple, plain quadratic equation, x squared. But we're going to look at quadratics, and here I'm going to pull up our notes and get us started with our notes. We're going to look at quadratic equations. Boy, and the handwriting's a little rough today, but I'm just happy to be here. Quadratic equations in a couple of different forms starting out here. We have the standard form, which is ax squared plus bx plus c, right? And we need it in this form for factoring, to use the quadratic formula. There's lots of reasons that we would want to have a quadratic formula in that form of ax squared plus bx plus c. But we're also going to be looking at the vertex form of a quadratic equation, the vertex form. So with the vertex form, let's see if I can highlight that and still read it. Yeah, that's pretty good. With the vertex form, it's a, this is a coefficient. Let me make that look a little bit more like an a maybe. A times x minus h in parentheses squared plus k. And when we have it in this form, that's going to make it real easy to tell what the vertex is. And we'll get more into that as well. But that's the two forms of quadratic equations that we're going to be looking at heavy in this lesson. And we can even convert from one to the other. So that is where we're going to be starting today. So then the general form of a quadratic equation is ax squared plus bx plus c. That's what I just wrote in our notes. So the graph of a parabola illustrates a quadratic equation in standard position. So that if the variable x is multiplied by a number a, so instead of having x squared, if we had a coefficient out front, like 2x squared or 5x squared or 10x squared, how would that change the graph? How would it change the graph? Well, let's play with that a little bit. Y equals x squared. All right, there is the standard. You know, it had the points, what was it? Negative 1, 1 is on the graph. The point 1, 1 is on the graph. We said negative 2, 4 was on the graph, which means 2, 4 is also on the graph. You know, so all of those points are on the standard graph of just a standard parabola. Oh, Cameron, I'll help you with that. We'll get to that in a minute. I'll get that fixed for you. So there's the standard. What happens if this x squared has like a 3 in front of it? How's it going to change the graph? Well, let me make a second graph that has a 3 in front of it. 3x squared. Oh, it got skinnier, thinner. You still see the points on the y equals x squared, but suddenly the 3x squared is going up a lot faster. What happened to these points? This point, there was a 1, 1. If we look at it, is actually, it's right up here at 1, 3 now. The y is 3 times larger. We still have the same x. We still have 1. When the x equals 1, here, and I'm going to change that to depths of 1 here on our scale so we can see that better. X is 1. Y used to equal 1, but now with a 3, we're multiplying it by 3. Now it's jumped up to 3 on the y instead of 1. If this was a 5x squared, take a prediction. It'll be about 1, 5, right? There it is. It's up at 1, 5 now. Oh, there it is. Because the y is growing 5 times faster for each x, because we put a 5 in front of it. So putting a coefficient in front of our x squared is going to make the y go up faster, which makes it skinnier. It's pulling it upwards. It's what we call a vertical stretch. We're stretching it upwards. If we're talking about horizontal, it's a horizontal squeeze because we're squeezing it in, but it's a vertical stretch. So that just helps us understand what happens when we put a coefficient. What if, oh, let's do this. What if that coefficient is less than 1? Maybe we put a 0.3 x squared. 0.3. Oh, look now. That y that was up here now is at 0.3. See, it's growing slower. The y has come down. The y has come down 0.3 instead of 1. So if it's a less than 1 coefficient, it's a horizontal stretch or a vertical, squeeze. We're squeezing it down vertically. We're stretching it horizontally. We really talk about vertical stretch or horizontal stretch. We're stretching it outwards. So that number in front of the x squared is going to affect whether it's skinny or fatter. Now this one's fatter. It's a lot wider than it used to be. So they're playing with it. If the a is bigger number, it gets skinnier. If it's less than 1, or if it's negative, it goes down. We didn't even talk about that. If this is a negative value out front, it reflects it downwards because we took the whatever the y was and we multiplied it times a negative. So that coefficient controls skinny and wide and also up and down, up and down, up and down. All right, it could be, here's the vertex form that we have. A times x minus h squared plus k. We don't know what's the a, the h, and the k represent. Well, let's play with that. Right now, we'll take this off. We've got this x minus h squared. I'm going to take these points off because that was illustrating stretching. If I put this x in parentheses, and I put a minus h inside of it, and let's say h is 4, minus 4. We can put an a out there, but let's put an a of 1 because I don't want to affect it. We know what a does. When a is bigger than 1, it's going to be skinnier. When it's less than 1, it's going to be wider. If it's a negative, it's going to flip it upside down. But in that vertex form, the a, we know what the a does. We just looked at that. Now let's look at what the h does. When I put a minus h in here, look what happened to it. Instead of the vertex being here at the origin, it has moved over. Let's leave that x squared equation there. There's the original. Now it moved over 4 because that's what h equaled. 4. What if it's a negative 1? What if it's a negative 7? Negative 2? What if h is a negative number? All right, I'm going to say h is negative 2. X minus negative 2. That made it move over to the left. Negative 4. Negative 3. Now here's the thing. You won't see it look like this because if it's x minus negative 3, how do we write that? X minus negative 3 means it's x plus 3 because when you subtract a negative, it's a positive. So x plus 3 moves it left because you're subtracting a negative. So that h, if there's an h value, that's going to move it left and right. Left and right. Now what about the k? Let's make h equal 0 now. Okay, h is 0. We're not moving it left or right. It's just our original equation. But now we want to check out this plus k. What does it do with the quadratic? It does the same thing it does to linear and every other equation you've ever looked at. If you add a number to the end, plus 3, it moves it up 3. Every graph you've ever done, if you stick a number on the end, it changes the y-intercept to that number. The y-intercept was 0. That's what crosses the y-axis. I added a 3. The y-intercept is at 3 now. It just moves the graph up or down on the y-axis. If this is a negative 5, wow, what do you know? The y-intercept is at negative 5. So that number on the end is pretty easy to predict. So let's put that on our notes to help us understand the vertex equation. A skinnier or wider. Like if it's greater than 1 or less than 1. A could be negative. Then it reflects downward. Let's see. H moves left or right. K moves up or down. So all of that is right here. A, which is right here. We've got X, which is right there. Oh, not X, H. H moves it up and down. And the K, let me get a nice, some kind of highlighter for K. We'll do this pink. K moves it up and down. This green highlighter is kind of funny. That's a little better. H moves it left and right. So the A, the H, and the K affect it like this. And this is all about the A right here. Skinnier, wider, up and down. If it's a plus, it moves up. If it's down there, H is the opposite. If it's X minus H, if it's X plus H, because the H is a negative in that case, then it moves. This moves to the left and right. This is a negative. This one is a positive. If it's a positive, it moves left. If it's a negative, it moves right. With K, if it's positive, it moves up. If it's a negative, it moves down. Get back over here. So this is called a translation from standard X squared.
Are you gonna post what you just wrote into the thing? I just couldn't get it all down.
Oh yeah. I'll take pictures of it afterwards.
Okay.
I'll go to the
Thank you.
classroom because there's a lot there. But here's additional review in the slope form of it. We're going to talk about linear equations much, but if you need to go back and review the slope intercept form, mx plus b, the same translations apply. If you put a plus k on the end, if it's -2, it moves down 2. See, it crosses the -2. 3 made it go up faster, made it steeper, just like it made a quadratic steeper by having that number in front of the x. So shifting the function of f of x equals x squared plus c inside the parentheses is basically like the x plus h or x minus h. That moves it left and right. Left and right. The plus c on the end moves it up and down. It makes it the plus k. Multiplying x by a number, it'll have a constant multiplied by the x. The graph becomes narrower or skinnier. And as the constant decreases, it gets wider. Same thing, putting c outside, just multiply the entire thing, can affect the horizontal and vertical shift as well as the width, depending on where your multiplication is. Like with -5 being outside, you'd have to distribute it, and it could affect more than one thing. What happens if we have a number multiplied by the whole function, like b times f of x? So if it's 2x plus 2, you're multiplying everything by 3. It becomes 6x plus 6, which it would make it go up and get wider. It affects the whole thing. I'm not going to spend a lot of time with this. We've got too much to cover. But if you're struggling with any of this, at some point you should come do this. Like right here, there's 7 of these. We'll do like 1 or 2. What happens with this? It's got -2 times x minus 4 squared plus 3. So is that going to open up or open down? Well, the first coefficient, the a, is a negative number, which means it's going to open down because it's a negative number. Is this going to be a narrower or wide compared to the original x squared? Well, 2 is bigger than 1. It's not less than 1. It's not a fraction. Even though it's a negative, it's still a number that's bigger than 1, which makes it more narrow. It's going to grow faster. Does this move up or move down? Well, we have to look at the end where we added 3, which means we moved the y-intercept up. And did this move left or move right? This is the one that always gets you, that x minus h, because it's opposite. If it's a minus, it moved right. Moved right. See if that's right. It is. We categorized it. And there are 7 of those. So go look at these and see, can you do that? Let's say, oh, this is up. It's narrow. It goes down and it goes right. Nope. Try again. See if you're just guessing. Let's see, what did it want us guessing at though? How about it's wide, not narrow? How about that? Too many incorrect attempts. So then it goes through and tells you everything. The coefficient in front of the parentheses opens the graph up if positive and down if negative. Well, that one's up. If it's greater than 1, the parabola is narrow. It is narrow. If the constant being added to the x inside the parentheses, the parabola moves left. If it's being subtracted, it moves right. So that one moves left. If the equation ends with the constant being added, the parabola moves down, or subtracted, moves down. Well, that should be right now because it does move down. Okay. According to this, it looks like we're correct on everything. It is up, it is narrow, it moves down, and it moves left. So I don't know what I wanted, but it says too many incorrect attempts. So we'll see what it tells you. Page 2. We got to get going. Parts of a parabola. Oh gosh. Okay. Let me write these down. Because these are the things that a lot of times on the questions we have the assignments going to ask you to identify these. Let's see. I'll get all this and then I'll switch where you can see it, but I got to copy it off the screen. Vertex, axis of symmetry, the domain, the range, x and y intercepts, and that's a sometimes. And it wants us to use this sample problem of y equals negative 2x minus 5 squared minus 8. Oh, good. Gave us a sample problem. Okay, so the parts of a parabola. The vertex, the axis of symmetry, the domain, the range, sometimes the x and y intercepts. Why do I say sometimes? Because sometimes there are no x-intercepts. If all the solutions are imaginary, if this is a parabola that's had a plus 10 on it and it's been moved up to where the vertex is way up at y equals 10, it may never come down and touch the x-axis. It might not have an x-intercept. So that's all the parts. And it wants us to explore that using this. So can we name all the parts of this parabola? What is the vertex? Well, that's the nice thing. This is the vertex form. This is the vertex form, which means when you have the vertex form, it tells you the vertex right in the equation. The vertex is HK, which for this equation, remember vertex form is x minus h. This is x minus 5. So our h must be 5 plus k. Well, it says minus 8. K must be negative 8. Okay, Mr. Bruck, you said this was negative 8 because this is negative 8. Then why is this 5 if this is negative 5? Shouldn't it be negative 5, negative 8? Just like, I see something wrong here. Well, the thing is, you have to look at the original. It's x minus the h, but it's plus the k, plus whatever the k is. So this is actually plus negative 8. It's got to be plus negative 8. That's the only way you can hit plus k. K is negative 8. That's why it's minus 8. H is 5. That's why it's x minus 5. If h was negative 5, this would be x minus negative 5, because it's x minus whatever the h is, which would be x minus 5 is x plus 5. I mean, because you're subtracting a negative. X minus negative 5 is just x plus 5. If this said x plus 5, we would have to know h must be negative 5. But that's not the case with ours. Ours is not a positive, so it's x minus 5. This is our vertex. What's the axis of symmetry? We haven't really talked about that yet today, but it's not new to your math minds. What is an axis of symmetry? Well, it's what divides something exactly in half. It's symmetric. Like if I have this ball right here, this rubber band ball, there's a rubber band inside the ball. I'm going to take the rubber band ball out. Okay, I'm just going to talk about this plastic ball here. This plastic ball. If I line this up perfectly, you can see the axis of symmetry is that line that goes right here and divides it perfectly in half, where this half is exactly the same as that half. It's a different color, but there's an axis of symmetry right down the middle of that circle, right down the middle. If it was over here, this is not an axis of symmetry because this side is smaller than that side. You have to line it up where it's exactly in the middle and cuts it in half. An axis of symmetry. You can even do that with shapes that aren't perfectly circular, like this could have an axis of symmetry. So what would that axis of symmetry look like? It's whatever line you can draw that makes this side a mirror of that side. Forget the color. The color doesn't help. But if you took a pen and you said, okay, I need to find an axis of symmetry. Okay, well, if I go right down the middle from like there to there, that could be an axis of symmetry because everything to the left of this side has a mirror image on this side, same distance. This point is exactly the same distance away as this point. This point's the same distance away as this point. Even up here, axis of symmetry. Everything over here is exactly like it is over here. It's just like a mirror has been put up. That's an axis of symmetry. So it doesn't have to be a parabola, but with a parabola, if we drew a parabola, it has a natural axis of symmetry right in the middle. The line right in the middle, that this side is a reflection of that side. And that always goes through the vertex because the vertex is the lowest point or the highest point, right? This is the vertex. The vertex is either lowest or highest point, and it's always right in the middle. It's the same going either direction. So if our vertex is at 5, negative 8, our axis of symmetry is wherever x equals 5. Oh, let's look at that. Let's graph this because we're going to want to do that in a minute anyway. So if we took our equation, y equals, let's see, what was it? -2 x minus 5 squared minus 8. Okay, that was, where's it at? There it is. It's way down there. It's down there. And we said that the vertex was at 5, -8, which there it is. That is the vertex, 5, -8. And that axis of symmetry would go right through there. So all we have to do is take whatever the x value is and say the line of x equals 5 is the axis of symmetry. If you know the vertex, the axis of symmetry is easy. It's whatever the x is, x equals 5. That line that goes everywhere that x equals 5 is the axis of symmetry. Oh, I like it when it makes it easy for us like that. So this is always going to be the same number. What is the domain and range? Well, the domain is the x's, and the range is the y's. That's not new. That's always been true. All the x's. What are all the x's possible with this parabola? Well, I see that it's getting wider and wider and wider. And if you keep zooming out, it'll keep getting wider and wider and wider. So it's getting both directions. It's going towards negative infinity and it's going to infinity. And as fast as it's going down, I'll have to zoom out a long ways to show that it makes it to infinity and it makes it to negative infinity, but it does. It'll make it to negative infinity and positive infinity. Eventually, it'll just take a really long time to get there. But we're not limited. It's not like at some point it's not going to get any wider. It will always get wider and wider and wider and wider. So we say our domain is negative infinity to infinity. Or you could say all real numbers. There's multiple ways you can say that. All real numbers from negative infinity to infinity, whatever you want. But what about the range? Does the range go from negative infinity to infinity? If you need to, look at the graph again. Well, the y's definitely go down to negative infinity, right? They keep going forever. That'll make it negative infinity. But what's the largest y this graph ever hits? It doesn't even hit 0. Look, there's no graph up here. Never hits -4, never hits -6. This is the highest point ever that this graph is going to be at. -8. So basically, it'll go all the way down to negative infinity, but the highest it's ever going to be is -8. And I guess I should make that a bracket because a bracket means it includes -8. Parentheses means it doesn't include it because you can't say it includes infinity or negative infinity because that goes on forever. So they always use parentheses with infinities. But with a number, it's like, does it touch -8 or not? Yes, it does. So we got vertex, we got axis symmetry, we got domain, we got range. We need the x and y intercepts. Y intercepts. Well, we just looked at it, and one thing we saw right away is this one does not have x intercepts. It never touches. None. None. There are none. It doesn't touch the x-axis. What about the y-axis? Yeah, it'll get there eventually. We just got to keep moving down until we, oh, somewhere right around here. Oh, there it is. -58. It's at the point 0, -58. So there we go. We found all the parts of this parabola: the vertex, the axis of symmetry, the domain, the range, and the x and y intercepts. Here is all of the answers for that problem. That's what it wanted. Now with this form of the equation, we could not tell the y-intercept without graphing it in this form. If it would have been in standard form, whatever c is the y-intercept, right? Ax squared plus bx plus c. Let's illustrate that real quick. Let me take this off the board. Let's just go back to a normal quadratic equation. Y in standard form. I mean 3x squared minus 4x squared minus 4x plus 6. Oh, there's the y-intercept. It's the plus 6. If this is minus 15, oh, look, there's the y-intercept at minus 15. When you have an equation in standard form, the y-intercept is always going to be the part of the equation that does not have an x, because the x equals 0 right here. So 3 times 0 squared minus 4 times 0, these are all 0. All that's left is the y-intercept, negative 15. All right, so finding the vertex, it goes through how to do all of that good stuff and to figure out all these things. Axis of symmetry, we covered that. Here's another example talking about the axis of symmetry. The domain, it's all the possible x's. Talked about that. The intercepts, easy to see when you're graphing quadratics. Does it have an, this one does have x-intercepts. These are not really nice over here. It's negative 1.666, which means it's negative 5/3 and 3. And negative 15 is the y-intercept. But you can graph and see, does it have an x-intercept or not? It may not. Here's what we have not talked about. Let's look at the graph of this equation again. So I'm going to go back and put this one back on there. Negative 2, because this is something that sometimes we struggle with. Okay, I'm back to that original graph. And it says the average rate of change. Well, if you remember that term from when you first learned it, that's the same as slope. What is the slope? Yeah, that's right. It's the slope. But how do you find it when it's not a line? Like, wrong screen, this screen. That's not a straight line. It's easy to find the slope in a straight line, right? When we have y equals 2x minus 4. It's like, yeah, what's the slope of that line? Oh, well, that's not hard. You'll find 2 points on the line, and I just do rise over run. Rise over run. So this rows for, what is that doing? That's not, there you go. It's supposed to be 2x. I do rise over run. So it rises from negative 4 to 0. 1, 2, 3, 4, and it goes 2. 4 over 2 is 2. So the slope's 2, which we can tell that because the 2 in front of the x anyway. But it's easy to do that. This is like, what's the slope between a couple of points? Well, let's see. Then when I find the average change from x equals 5 to x equals 6. Okay, let's zoom in here a little. When x equals 5, that's the point negative 8. What is it when x equals 6? It's negative 10. So 6, negative 10. And we said it was at what? 5, 8, and negative 8. So what's the slope between those 2 points? Well, if we look at the parabola, the slope is changing everywhere. This is pretty slow, but it's getting pretty steep right here. Average. If we could find every little number in there and take the average, it would be the same slope as this. Yeah. Take a straight line. We do this. 5 less than x less than 6. It wants to know what's the slope of that line. If we take a straight line and draw it from 5 to 6, the average would be exactly what the slope of that straight line is. That's the average rate of change. And we can find that by just doing rise over run. What's the rise? Well, it goes down 1, down 2, so that's negative 2. And the run is it goes 1. So negative 2 over 1, the average rate of change is negative 2. How about that? So if you can find out what those points are, you can also use the slope formula. Remember the slope formula? y2 minus y1 over x2 minus x1. So if we said, let's see, the 6 was at negative 10, and we subtract from that negative 8, because that's the other y, and then we're subtracting 6 minus 5, because that's what the x's are. When x is 6, y is negative 10. When x is 5, it's negative 8. Negative 10 minus a negative means plus 8. Negative 2. 6 minus 5 is 1. Negative 2 over 1, that is the slope. That's what m equals. Between the points 5 and 6, the average rate of change, or the slope between those 2 points, is negative 2. That is something you learned to do a couple of years ago. This is not new. It's just that it confuses you when you are not looking at a line. You're looking at a parabola. And it's like, oh, I don't know what the average rate of change is between those 2 points. Well, you do, but you're thinking of it wrong. You're thinking of it, oh my gosh, how do I got to do this with the curve? Forget the curve. We're just looking at those 2 points. We're not even looking at that. We're just knowing from this point to that point, what is the slope? You can take this out of the equation. We don't need the parabola. We just need to know what the parabola equals at 5 and what the parabola equals at 6. And what's the slope between those 2 points. That's what average rate of change is right there. Rise over run, or the slope formula, but you get to negative 2. So the average rate of change from x equals 5 to x equals 6 is negative 2. All right, we are over halfway through our time, and we're only on page 3 of the first lesson. You've learned a lot about the parts of a parabola, vertex equation, all this stuff. We are going to watch this because she is not really talking about how to graph all of this in the traditional sense, like making a table and all that stuff. And this is a short video, so I do want us to watch this to get her thoughts on how do you graph this. And you get to meet like Basketball Betty or something. I think that's her name.
Hello, today we're going to graph quadratics. So let me introduce you first to Betty Basketball. She's getting ready for her finals, and she's determined that if she stands this far away from the basketball hoop, she'll be able to make a basket. So here we have the equation based on this parabola. Y is equal to negative 3 and then x plus 2 squared plus 4. Since it's already in vertex form, we can go ahead and plot our vertex. It is going to be at negative 2 and 4, and notice that there's a negative up here, so that means it's going to face downward. If I go over to my graph, I'm going to plot my point at negative 2 and 4. The next thing I want to do is I want to figure out the y-intercept. So I'm going to go ahead and change this to standard form. So y is equal to negative 3, and then I have x plus 2 times x plus 2 plus 4. Notice that I'm squaring my binomial, which is why I have it here twice. The next thing I'm going to do is use the distributive property and multiply my binomials. So y is equal to negative 3, and I have x squared plus the 2x plus the 2x plus 4, and then we still have this plus 4 out here. I'm going to go ahead and combine my like terms inside the parentheses. So y is equal to negative 3, and then x squared plus 4x plus 4, and then a plus 4. I can distribute my negative 3, so I have y is equal to negative 3x squared minus the 12x minus 12 plus 4, and then I have one more step, which is to combine my like terms. So y is equal to negative 3x squared minus 12x minus 8. So to find the y-intercept, remember that we substitute x is equal to 0, and we know that our y-intercept is going to be at negative 8, which is our constant. So I'm going to go ahead and plot my y-intercept, and I'm going to draw my parabola. Remember, it's a skinny parabola because of the negative 3. And remember, it also should be symmetrical. So on this side, I'm also going to draw a thin line. And that's how you graph a quadratic.
That was pretty simple. Now that's really just, it's a sketch of a graph. It's not an exact graph, but all she had to find out was where was the vertex and tell me the y-intercept. With the vertex and the y-intercept, you can make a sketch of the graph. So that was pretty cool. That's why I like doing this. Now, there was something she illustrated in there that, let me see, I don't know what else was in there, that she illustrated that's going to be important. To find the y-intercept, she changed it from a vertex form to a standard form. And we're going to look at that in just a minute. Let me see what else is on this page. Elements of parabola, axis of symmetry, right? We talked about that. So any point that's on this side of the graph will be the same distance away on the other side of the graph. The domain and range, all the possible x's and the y's determined by the vertex. And then the intercepts, the x-intercepts and the y-intercept. And identifying the elements of a parabola. There's another example if you need it. I'm not going to go through all of that just because on the basis of time. Standard form of a quadratic equation. Okay, this is what she was doing, expanding the vertex form to find the y-intercept. So I want to go do that with our same equation that we've been using right here. So we could convert this. We said before we graphed it to figure out, oh, it crosses the y-intercept at -58. But we could do it algebraically without knowing that. So let's do this. -2 x minus 5 squared minus 8. That was our original equation. So in order to turn this into standard form, we just have to distribute. Simplify this. So we have -2 and x minus 5 squared. That's x minus 5 times x minus 5 minus 8. So we have to multiply these three things together and then subtract 8. So we can do them in any order. We can do the -2 first, or we can do these two first. Now let's do the -2 first, just to be different than what she did. -2 times x is -2x. -5 times -2 is a +10. And then we still have to take that times another -5. Another -x minus 5, sorry. So these two have been combined. Now let's take -2x times x is -2x squared. -2x times -5 is a +10x. 10 times x, +10x. 10 times -5, -50 minus 8. Now we just need to combine like terms. We have two sets of like terms. So this is -2x squared plus 20x minus 58. The y-intercept is -58 that we also found graphically. But we can do it just by changing this to standard form. Ax squared plus bx plus c. And the c is the y-intercept. You're like, okay, well, that's cool. This tells us the vertex. This tells us the y-intercept. And that's really all you need to know to graph at that point. At least that's just a sketch of the graph. It wouldn't be a perfect graph. Well, there's another shortcut that if we have this form, we can actually find the vertex with just a little bit of math. Let me see if they got that on this page. Expanding the vertex form of a quadratic equation. So that's going through the steps I just did. Combine all this to make it a standard form. Wait a minute. Oh, they had a +8. They had a different formula. Okay. I'm like, why is theirs different? They didn't use the -8. They did a +8. They used a little bit different formula that we were using. But finding the equation x equals negative vertex. To find the vertex, when we have it in standard form, the vertex, at least the x part of the vertex, is -b/2a. So this is actually x of vertex. Also, this is the axis of symmetry. So what is our equation? We got 20 as our b. So ours would be x equals negative 20 over 2 times a. Our a is negative 2. So 2 times negative 2 is negative 4. So a negative and a negative cancel each other out. 24 is equals 5. So x equals 5 is the axis of symmetry. And the x vertex is going to be 5 something. Because remember, the axis of symmetry goes through the vertex. Well, we did find the axis of symmetry was x equals 5. But we found it from the standard form down here, where this we found it from the vertex. How do we get what is the y? We have the equation right here. If we said negative 2 times, what's the x? The x is 5 plus 20 times 5 minus 58. Substitute the 5 in there and see what the y equals at that point, at when x is 5. 5 squared is 25 times negative 2. That's negative 50. 20 times 5 is 100 minus 58. Negative 50 plus 100 is plus 50. Plus 50 minus 58 is negative 8. Huh. This is the exact same vertex that we found from the vertex form, which was 5, negative 8. But when we have it in standard form, we've got little tricks and shortcuts that we can use. That's the axis of symmetry, but it also gives us the x of the vertex, because it's the same thing, and we can get 5, negative 8. Great shortcuts to get all of this information, because that's what our questions are going to look like. Hey, tell us all this information. Like we get to the test, it'll have a question probably. I don't remember. I know I've seen this. Tell me all this information. Well, you can get it from the vertex form. You can get it from the standard form. And then, of course, a lot of it you can get from graphing. But that's pretty cool. All right. Finding the axis of symmetry. There is x equals negative b over 2a. That's the equation of the axis of symmetry. So in this case, it was 5. And then you can take that 5 to figure out the vertex, which would be at 5, 8. So here's an example problem. If you want to see if you can do this, I'm about to move on to the next lesson, but if you want to see if you can do this, identify the axis of symmetry, vertex, domain, range, and the intercepts of this equation. And it'll walk you through how to do that. All right. Learn more. Here's another example. If you want to try that one, let's go to our last page of the lesson, because there's practice problems after this page. Can you reverse this and build the equation from the graph? Well, that's probably a pretty good sample thing to do. Let's see. So if we had this graph, can we build the equation? Let me write down what we can tell from the graph. We know what the vertex is, right? The vertex is 1, negative 2. What is the y-intercept? The y-intercept is 0. And is there anything else we need to know? Let's see. It goes up, so we know it has a positive. So let's take what we know so far. We know the vertex. So with the vertex form, which is y equals, I don't know what the a is going to be, but x minus h. H is 1. X minus 1 squared and minus 2. The only thing we need to know is there an a? That's the only thing we haven't figured out. But this is the equation because it goes through that vertex. That's h and k. And the y-intercept being at 0, 0. Let's see. So 1, negative 2. So we know that the 1 and the 2 works there. Let's see. What else do we know? No. Oh, there's a 0.36. Okay, let's see how that works. I was using the 0.00 as well, but they had this 0.36. Okay, this is a good way. If we look at the graph again, let's just use 36. So you can graph it if you find a point on the graph. So 36 is on graph. It probably work with 0 also because that's also on the graph. Is on graph. This will help us figure out if there's an a, what a equals. So take the y is 6 equals a times the x is 3 minus 1 squared. Okay, and solve this for a. Since we know this point is on the graph, the a would affect getting us there. So let's see, we need to get rid of the 2 first. So we've got 8 equals a. 3 minus 1 is 2. 2 squared is 4. So we've got 8 equals 4a. So if we divide by 4, a equals 2. So our equation should be y equals 2 times x minus 1 squared minus 2. Because when we substitute in and just simplify it down, we got a equals 2. Let's put that in Desmos and see if that actually goes through the 0.36 and has the correct vertex. So we said that y equals 2 times x minus 1 squared minus 2. There's the vertex we had, right, at 1, negative 2. Does this go through 3, 6? Label that. It does. This is the correct parabola because it has the right vertex and it goes through the 0.36. There's the 0, 0 point that it also has on the graph. So that is the correct way to find the entire equation, just knowing the graph. Well, that's pretty slick right there. All right, so, and they walk through all that again if you need that. Here's the lesson summary that talks about everything that we just looked at. We got about 25 minutes to do completing the square. All right. There are practice problems here. If you're like, Mr. Brock, I need more practice with this, you bet. Here's practice problems here. Graph this equation. Tell me the vertex, the equation of axis of symmetry, the domain, the range, the x and y intercepts. And then after you do that, see if you're right. Here's all the answers. Problem 2, same thing. Graph this equation. This one's in vertex form. Identify all those things again. Check your work. There's the answers. Here's more practice problems. Graph this equation. Which one of these is the correct vertex? Which one of these is the correct axis of symmetry, domain, range, x and y intercepts? There you go. There gives you that. And there's 3 problems there. Calculate the average rate of change. Oh, yes, please. From negative 3 to negative 1. Well, at negative 3, it is equal to 0. At negative 1, it's equal to 0. What's the slope between those 2 points? 0. I just go straight across. There's a couple of those problems. Average rate of change. All right, page 7 has some more sample problems. Oh, here's another one. Identify the vertex, axis of symmetry, domain, range, and y-intercepts. There are 5 problems that you can practice with right there. Here's some more. Question number 1, graph this. Graph this. So it's just a matter of graphing it, which we can do it with Desmos, so that's not a real challenge. This is if you're doing it on paper, might be a little bit more of a challenge. But anyway, let's look at the assignment real quick for this. So our first assignment, identify the vertex, domain, and range. There's the graph. What's the equation for this graph? in vertex form. Oh, that one's going to be real easy because A is 1. All you have to do is look at the points they gave you and choose the correct vertex form equation. Which of the following represents a function opening downward? If f of x is x squared and k is -1, where would we put the k to make it open downward? What's the average rate of change from x equals 3 to x equals 5? Don't make that hard. Determine the axis of symmetry for this function, and it's in vertex form. So those problems aren't bad. Those aren't bad. I like those. Okay, I know I haven't done it yet. Well, let me look at the next thing. Did I ever fix that? Yes, it'll let me look at the next thing. All right. Oh, we're not going to watch the little video. We don't have time for that. You can go watch the little video if you want. It's about an orchestra. After completing this lesson, you can answer this. How can completing the square aid in solving quadratic functions? And what indicators predict it'll have a complex solution? So let's look. Here was the vertex form that we just looked at. And the quadratic equation written in this manner describes the graph without a whole lot of explanation or detailed mathematical work. We can take this equation and we can find the vertex, right? It's HK. We can find the axis of symmetry. It's x equals h, whatever the h is, x equals 5. We can find the domain, all real numbers. We can do a description of it, opens upward. The range, we know it's from the vertex. And we can find the y-intercept mathematically or graphing it either way. But here's a review on converting from vertex to standard. Now we did that where we just distributed it, multiplied it out, simplified it, and we could turn this into standard form. We did an example like that. Completing the square is going to give us the ability to go the other direction. No way, Mr. Brock. Yes, way. So we're going to learn how to convert the quadratic equation to vertex form, starting with 2x squared minus 20x plus 47. So let's write this down. This is going to be amazing. Let me sharpen my pencil. So I start by setting it equals to y equals 2x squared minus 20x plus 47. The first thing I need to do is take this 47 and move it to the other side. So I've got y minus 47. I just subtract it from both sides, equals 2x squared minus 20x. Okay, so far so good. All I did is move the 47 to the other side by subtracting it from both sides. Now I'm gonna factor the greatest common factor out of this, but only the coefficients. I need those x's. So I'm only looking at it. There's a 2 and a 20, which means this is y minus 47 equals 2 times, so I can factor 2 out, x squared minus 10x. I just factored the 2 out. I could have factored an x out, but I need the x for what I'm doing. I need the x. Okay, what I want to do now is to make this a perfect square trinomial. You're like, make it a perfect square trinomial. Yes, make it to where I can multiply 2 binomials together or the same binomial squared, because I want these to be the exact same binomial. I want it to be the same binomial squared. I need to make this a number on the end that I could do with that. And here's how I'm going to figure that out. So let me give myself a little space here to add to this. I'm going to take this coefficient, -10, and I'm going to divide it by 2. That would be -5. Agreed? -10 divided by 2, -5. That's the easy part, not hard. Then I'm going to square that. What is -5 squared? -5 times -5, 25. I'm going to add a 25 on here. But if I do that, I also have to add to the other side because I've changed it. These are not equal anymore. These were equal. This is not equal. How much did I just add? You're going to say I need to add 25. That's wrong. I didn't add 25 because everything inside here, ooh, got to emphasize this. Everything inside here is being multiplied by 2. I just added 50. I added 50 to this side. I've got to add 50 to this side. Now these are equal again. I added 50 over here. I added 50 over here because everything in here is being multiplied by 2. So if I add 25, I'm adding 25 times 2. Now I know that this is 2x minus 5 squared because I made it a perfect square trinomial by completing the square. This is the number I used, so that's the number that goes here. When I cut that in half, that's the number that's here. You're like, how do you know that's that, Mr. Bruck? Well, we need to prove that to ourselves. See, it's x minus 5 times x minus 5 or x minus 5 squared. And we can prove that that worked by multiplying it back. X times x is x squared. X times negative 5. Negative 5 times x. Negative 5 times negative 5 is plus 25. Simplify this. These are like terms. X squared minus 10x plus 25. Hey, that is x minus 5 squared. Because when I multiply x minus 5 times x minus 5, that's what I get. Completing the square, making this a perfect square trinomial. So over here I've got y minus 47 plus 50. Over here I've got y plus 3. All I have to do now is move this 3 back. Minus 3 minus 3. Y equals 2x minus 5 squared minus 3. This is the same equation as this. This is standard form. This is vertex form. By completing the square, I can go from standard form to vertex form. If I want to go from vertex form to standard form, I multiply it out like I did here. Where'd we end up with? Right there. Negative 2x squared plus 28 minus 58 is the same as this. On this one, we went from this standard form. And now let's prove that these are the exact same equation. How do we do that? We go graph them both. If they have the exact same graph, they must be the same equation. Y equals 2x squared. Oh, I didn't get the shift x. They were 2x squared minus 20x plus 47. Okay, so there is the graph of the first one. Now let's graph the vertex form that we created. 2 times x minus 5 squared, and I said minus 3. Looky there, they are the exact same graph, so they must be the exact same equation. That is pretty cool. So this walks through the steps of doing that, what I just did on paper. So if you need to look at that on how they did it, they ended up with the same vertex equation. Important note, once the equation is isolated the y variable again, it is appropriate to replace it with an f of x. We can call it f of x equals 2 times 5 minus x squared minus 3. Instead of leaving it in y, we'll put it in function notation. Certification on why do you divide that middle coefficient by 2 and square it? A perfect square trinomial has a middle coefficient that's equal to twice the product of the square roots on the end terms. So the opposite of doubling a number would be dividing by 2. So that's why we divided by 2, because when we went the other direction, we took it times 2. And the opposite of taking the square root is squaring. This is called completing the square. So I do want to do this exercise real quick, because this is the part that gets a little tricky. I'm going to make this a little bigger. I want you to put it in the chat. Let's not waste time. We don't have a lot of time, guys. What number would I need to add to make that a perfect square trinomial? All right, before you get so excited again, it's like, wait, Mr. Brock, I don't remember. Let me review this real quick. The way I figured out which number to add here is I took the number here, divided it by 2, and whatever that number equaled, I squared. So 25 was the number I came up with. I took the -10, divided it by 2, which gave me -5, and I took -5 and squared it, which is where I got the 25 that I added. So knowing that, x squared minus 2x plus what? See, so Sophia says if you take that 2 and divide it in half and then square it equals 1. Oh, a lot of people saying 1. Submit. Excellent. All right, let's do another one. How about this? X squared plus 8x plus something. You make this easy. Now remember, the only thing that's tricky is you have to add it to the other side of the equal sign too. But knowing what number to add is a big part of it. Yes. Minus 14x, x squared minus 14x plus something. Oh, Cameron, you're quick on this. Saha's got it. All right, I got 2 folks really quick with this. Take that in half. You can put the negative if you want to. -7 or 7, both square to be the same number. So -14 or 14, cut it in half, 7, square it, it's 49. 24. 24. Cut it in half, 12. 12 squared. Hopefully you know your multiplication tables. Our last one, 30x. Oh, see, this is a little trickier. We get outside of our normal 1s through 12s multiplication tables. This is slowing you down a little bit. There you go. 15 squared. 15 squared. Yeah, 15 squared is 225. It is. It is. Perfect. All right. Good job. Good job. All right. I do want to do another sample problem. We got about 10 minutes. And we got to look at our assignment to go with this. It says we can evaluate the discriminant to see what type of solutions. Because the one thing to talk about also is finding the solutions. The discriminant is that b squared minus 4ac. That's part of the quadratic formula. And remember our chart that we made. See, do I have it here? They have the chart somewhere. I thought I saw it on here. Oh, there it is. Remember, if the discriminant is 0, we're going to have one rational solution. If it's a positive perfect square, like 3, not 3, I mean 4, 9, 16, 25, 36, it's going to have 2 rational solutions. If it's positive, but it's not a perfect square, it's going to have 2 irrational solutions. And remember, if a discriminant's negative, we're going to have imaginary solutions, complex solutions. So it has a reminder of that. So if we write this in general form, rewrite it, because both sides equal sign been manipulated, replace it with a y. So here's another one where they remove the 26 to the other side, complete the square with the 12x, cut it in half and square it. So they added 36, and you have to add the 36 to both sides. This time there's not a 2 outside with the parentheses, so just add 36. Simplify it to x plus 6 squared, and then move the 10 back, and you've got the x plus 6 squared minus 10. And then they check the work by multiplying it back together and finding, yes, they get that. Using the vertex form, is it a minimum or maximum? We can talk about that real quick. If we know that this is a positive coefficient with the vertex form, we know it's going up. If I ask you if the vertex is a maximum or a minimum, well, this is the vertex. Obviously, it's a minimum. That's the lowest point of the graph. If this was a -2, Let's turn off the other one. That was a -2. We know the vertex is a maximum because it's a downward facing graph. So bring up that point right here in this part of the lesson. I want to go to page 3, which is the last page of this lesson, because it said solve this by completing the square. All right, so we want to do this one more example. And I think I'm going to, I think I've got enough room here. So the first thing we're going to need to do is move the 8.
So we're going to work backwards. What do we need?
Y minus 8 equals x squared plus 6x. 6x. Cut it in half and square it. We're adding 9, which means we're also adding 9 over here. I kind of wrote, I didn't leave room. I was going to put it right here, but I didn't leave room. So plus 9. So over here, y minus 8 and plus 9 is just y plus 1. This is, we know, is x plus 3 because it's whatever this is when you divide it by 2. Move the 1. So the equation is y equals x plus 3 squared minus 1. But solving it, how do we solve this? Let's see, what steps did they do? I forgot how they walked that. So complete the square with the 3, balance the equation, add the 9 to both sides. Oh, they still got the y. Yeah, yep. Okay, that was the thing. I should have left this like the problem had it. If we're solving it, we don't have a y. If we're solving it, we set it equal to 0. That's the way you solve quadratic equations. So it equaled -8. I added 9 to both sides, so now it equals 1 when I add 9. So I've got 1 equals x plus 3 squared, which doesn't mean that I don't necessarily need to do this. I'm sorry, led you guys astray. Just scratch that out or something. If we're solving, we've got to set equal to 0. That's the part I messed up on. I shouldn't have put a y. X plus 3 squared equals 1. Okay. So that's the point they're at. X plus 3 squared equals 1. So now to solve it, we got to get rid of the square. Right? We're trying to solve for x. Well, the way you get rid of a square is you do the opposite, which is square root. Which, let me write it up over here now. So this side is the square root of 1. And this side is now, these cancel out. So this is just x plus 3. So if I subtract 3, subtract 3, I have x equals, and this is plus or minus. When you take the square root of something, it's plus or minus, right? This one canceled out, so there wasn't a plus or minus. Plus or minus the square root done. So the answers are 3 plus the square root of 1 and 3 minus the square root of 1. Those are the two solutions for that quadratic equation. 3 plus the square root of 1. Well, what is the square root of 1? Square root of 1 is just 1. So it's 3 plus 1 and 3 minus 1. So x equals 2 and 4. Because the square root of 1 we can actually calculate. But I'll show you this way, because if it was like the square root of 2, that would be the final answer. We can't simplify that, but we can take the square root of 1. The square root plus or minus the square root of 1 is just plus or minus 1. So the answer should be 2 and 4. Let's check that. If we want to graph that, y equals x squared plus 6x plus 8. Oh, I hit equals instead of pluses. Oh, why is that positive instead of negative? Oh, I see why. Because I forgot I subtracted 3. I subtracted 3. So it's -3 plus or minus 1. -3 plus 1 is -2. -3 minus 1 is -4. So the answers are -2, -4. I forgot I forgot my negative. How many times I've warned, like that's where we make mistakes, right? We forget a negative. But we did this by completing the square. Now it was real easy to do by graphing because we can see that's the two solutions. But completing the square, check your solutions. So there's another example of solving one if you would like to look at that. We're out of time, so I'm not going to. Here's the lesson summary that talks about completing the square. And you can change it from standard to vertex by completing the square. And you can use the discriminant to tell, am I going to have two nice solutions, one solution, two imaginary solutions? Here's the steps. So if you want to write those steps down, you can, if you have a printer, you can print this out. So let's look at the assignment real quick. Determine the vertex, and this is in vertex form. Oh, thank you. That's easier. Which of the following values completes the square for this equation? I think you guys got that. You were nailing it in the chat. Using the completing the square method, rewrite this in vertex form. So this one, you actually just do the work. Complete the square, write that in vertex form. Find the vertex of this function. And is it a minimum or maximum? And what is the vertex? So convert this to vertex form. Then you'll figure out, does it go up or go down? So is it a maximum or minimum? What is the vertex? And do this, complete the square and solve it this time. So set it it's equal to 0. So move the 5 over, complete the square, solve for x. It'll be one of these. Whew, we were kind of like running like our pants was on fire today. Covered a lot of stuff, but there's a lot of good stuff in here. Quadratics, man, there's so much we can do with quadratics. All right, guys, I'm going to wrap up class here. If you got questions, this is a B-Day Friday, so we only have class on Wednesday, but I'll be in class on Wednesday, so you can come see me if you need anything. And I'll get our new student here, Cameron. I'll get you where it'll let you see stuff in Buzz, because that's a pain in the butt when it doesn't do that. So I want you to be able to get to these lessons and be able to do this. So have a great week, guys. I'll get Cameron fixed. We'll move on to the next day.